Hello, my name is Faisal. I'm going to explain problem one, which is the open loop simulation of a 2 degree of freedom robot manipulator. First, we apply two constant torques to the robot joints, which they are minus 0.76 and 0.63 Newton meter. These torques are sent to the robot dynamics block, which represents the physical model of the robot, and the block uses the dynamic equation of the manipulator to calculate the joint accelerations. Next, the accelerations are integrated to obtain joint velocities and integrated again to obtain the joint angles theta 1 and theta 2. The joint angles and velocities are then fed back to the dynamics block, because the robot parameters change with the robot configuration during motion. After that, the end-effector kinematics block calculates the Cartesian motion of the robot tip. Using the forward kinematics equations, it computes the end-effector position in the x and y direction. Finally, the scopes display the main outputs, which are theta 1, theta 2, xe, and ye, over a simulation time of 10 seconds. Looking at the results, the system is open loop, meaning there is no controller to stabilize the robot. Therefore, the joint angles keep changing under the effect of the applied torques and gravity. The end effector positives, xe and aye, also oscillate because they depend on the joint angles. However, the robot tip remains within the physical workspace of the robot, whose maximum reach is L1 plus L2 equal 1.1 meters. In conclusion, problem one shows the natural behavior of the robot under constant torque inputs without any control system. Thank you, and that's for all for my part.
For question 2, or for problem 2, we can see that we have our own constants and we have our own sinusoidals, and we have used the switch to switch between the constant and the sinusoidals uh, variables, numbers. Uh, um, in our in our problem 2, our goal is to control the position of the effector. So instead applying a direct, like what we have done in problem 1, we have given it like a desired reference, xe ref and y ref. Um, the Simulink for the Simulink, as I said, we have like constants and the sinusoidal, and we have used the switch to switch between each reference. And then it goes to the inverse kinematics. Since the motion is not like directly control the xe and ye, if we converted the desired end effector position into the desired angle, and then by using the inverse block, we can take the xy ref and convert it to theta ref, theta 1 refs. For after we convert it, after we get the thetas, we use a position controller. This is like telling us the difference position error. So like we compare the actual angle thetas. This error tells us the controller how far the robot is from the desired position in the error. If the error is large, the controller produces a large command. If the error becomes small, the controller command becomes smaller. For robot, I mean, yes, here for the derivatives, it's like used to add velocity and the damping effect. This helps us to reduce the oscillation and improve the response. So it act as the BD controller, and we will see it in problem 2. I mean problem 4. So in simple words, the controller uses the position error and the rate of change of error to generate the desired acceleration and torque command. And for the robot dynamics, when we move to the robot dynamics, the command uh, uh, the command after yes after for the robot dynamics, which is represent the robot model, uh, uh, we use the input torque and the joint angle and joint velocities. Joint velocities and the to and the robot dynamics block calculate the joint acceleration, which is theta double dot. Like we got the theta dot and theta from the integral and by taking the integrals for theta dot, theta double dot, and by taking the tau command, torque command from the disturbance block, like and basically the integral will integrate the theta dot by getting us the velocity and position. This is how we can generate our simulation. And for our disturbance block, the disturbance is added like to between the controller and the robot plant to improve the motion of it. Its job like to estimate the disturbance of air acting on the motors. It compares the desired acceleration with actual acceleration. If there is any difference, it can treat it as an estimated disturbance. The estimated disturbance passes through a low pass filter. This one. To filter and remove noise and prevent reacting to any strong acting on the motion. After it filtering the disturbance, it added a composition to our torque command. This has helped the robot follow the reference more accurately, even if there are model error, friction, or disturbance, or any external disturbance. Uh, so just the block is, or the disturbance observer uh, uh, improves the torque command before it enter our robot dynamics. And when we move to the end effector, after the robot dynamic given, after the robot dynamic gives us the actual joint velocity and acceleration, the end effector kinematics block converted to the certain motion. It calculates the xe dot and xe double dot, and same thing for the y and also for the thetas. Uh, when uh, when we run the simulation, we can see that there's two scopes, one that comes from the xe and one comes from the sinusoidal reference that we have chosen. Yeah, sinusoidals. And when we open it, we can see that the scopes like usually use we have the xe and the reference of the sinusoidal. The first scope shows the xe reference and the xe on the same graph. This is allow us to see the actual x position follows the desired position, which is, yeah, correctly for 10 seconds. And same for the y, also in the same graph for 10 seconds, and it follows the same path. And this is like become same to our reference signals. And this is basically what we wanted. And that's all for basically that's all for our problem 2.
Hello, my name is Obada Hashish, and I'm gonna explain the problem 3. The goal is to control the end-effector velocity. The desired velocity is minus 0.29 meter per second in the x direction and 0.02 meter per second in the y direction. Since these velocities are in Cartesian space, we use the Jacobian inverse to convert them into desired joint velocities. Then the controller compares the desired joint velocity with the actual joint velocity. The difference is the velocity error. The controller uses this error to generate the torque command. After that, the command goes to the robot dynamics block. This block calculates the joint acceleration. Then the integrators give velocity and position. The disturbance observer improves the torque command and helps reduce the effects of errors or disturbance. Finally, the schools compare the desired velocity with the actual velocity in x and y directions. From the results, there is some oscillation at the beginning. Then the response becomes more stable and closer to the reference. Tamam.
Okay, and now I'm Sajid and going to explain the problem 4. First of all, our goal was to make the robot push against the corner at the wall at x equals negative 0.05 and y equals 0.75 meters with a specific target force. The target was to pull left with negative 6 Newton in X and push up with the positive 5 Newton in Y. The environment acted like a passive spring and damper. It can only push back if hits cannot grab or pull the robot. Then what happened in the X, the wall, the collision at 1.5 seconds, the robot hit the wall, causing a massive brief force spike of 37 Newton. The mistake was the robot programmed to pull on the wall for negative 6 Newton. But because the wall is passive, it can only push back. You cannot pull on the surface that is not grabbing in. Finally, we have the result, which is the robot failed to reach its target and the force slowly dropped to about 1 Newton by the end of the simulation. And lately, what happened in the Y, the result was because it never touched the ceiling, the actual force maintained 0 Newton instead of the target 5 Newton. Finally, the physical remains. Finally, the physical realism matters. You cannot command a robot to build tensile force on a passive environment that cannot only push back with the compressive force. Thank you all for listening, and that's all.